In the last section, we focused on two of the DiVincenzo criteria, qubit coherence and quantum gates. We developed an intuitive figure of merit, the average number of gate operations that can be performed before an error occurs. Such metrics are important because they allow us to compare different qubit modalities, even when those modalities have remarkably different properties. However, the definition we introduced only accounted for errors due to qubit decoherence. That's fine for qubits that are dominated by decoherence, but some qubit modalities are limited by other sources of errors. For example, control errors, imperfections in the pulses that are used to drive a gate operation. For these qubits, even if their coherence times were practically infinite, their gates would still be subject to control errors. So what we need is a more rigorous way to characterize the robustness of a gate operation, one that's sensitive to a broad set of error sources. And that leads us to the subject of this section, a more general concept called gate fidelity. Gate fidelity is a rigorous means to define how well a gate operation works. Essentially, it's a measure of how closely our actual gate operation matches, on average, a theoretically ideal version of that operation. For example, if we apply an X gate to a qubit prepared in state 0, how close do we get to state 1? Now, intuitively, errors could occur along any direction of the Bloch sphere, and so we need to check for errors along all directions after the operation is complete. Until this point in the course, we've only measured the qubit along the z direction, but in principle, we can choose to measure the qubit along any axis that passes through the center of the Bloch sphere, including the x-axis or the y-axis. In addition, gate errors may be manifest differently depending on the starting point of the qubit. So we need to check how the gate performs against different initial states, and not just the North Pole, for example. Now, at this point, you may be asking yourself, how is this even feasible? The qubit state can be anywhere on the surface of the Bloch sphere, and that represents an infinite number of possible initial and final states. How can we possibly check them all? Well, in fact, we don't have to, and that's because we can define a basis set that spans the entire qubit state space. To draw an analogy, think of global positioning. Our position anywhere on the globe can be represented by projecting it onto a convenient basis. In this case, a coordinate system that spans the globe. We often use latitude and longitude, but we could equally well use Cartesian coordinates, x, y, and z. Similarly, we can define a basis that spans the entire qubit state space and then use it to specify any qubit state at the input. We can also use it to characterize any state at the output by projecting back onto this basis. This works because quantum mechanics is described by linear algebra. It's enough to understand projections to and from the basis set to know what will happen globally. And in fact, as we'll see later in the course, such projective measurement plays a crucial role in the digitization of errors and our ability to correct them. Although the coefficients of a superposition state will dictate the probability of obtaining a 0 or a 1 when measurement is done, for any given measurement, we will get a 0 or a 1. In this way, quantum states and their errors, which appear to be analog, can in fact be digitized through projective measurement. Now, we saw previously that n qubits can represent 2 to the n states. Here, the basis can be represented in a matrix form, and the number of matrix elements that spans the state space is the square of the number of states, so 2 to the n quantity squared. For a single qubit, n equals 1, and we need 4 elements. For 2 qubits, n equals 2, and the number quickly increases to 16. So determining the gate fidelity is essentially a standard black box type problem. We have a gate operation, and theoretically, we know how it should perform. However, due to errors, its actual operation isn't precisely known. That's the black box. And so we need to characterize, on average, how well our gate operation actually performs. To do this, we probe the gate operation using the input basis states, perform the actual gate operation, and then, for each input, project the resulting output state onto the entire basis set. We then compare our results to what we would expect from a theoretically ideal operation to determine the gate fidelity. The approach just described is called process tomography, and it represents a complete description of the errors during a gate operation. It also requires a large number of steps to implement, as the product of input and output elements is 2 to the 4nth power. Now, although there are 2 to the 2nth constraints due to the properties of these matrices, this only reduces the total number of measurements by a small amount. Thus, implementing process tomography scales very poorly with the number of qubits and becomes impractical as n gets large. This is an issue because although our gates only act on 1 or 2 qubits, the errors may cause leakage to other nearby qubits, qubit 3, qubit 4, qubit 5, etc. And so to account for this, the basis we choose must encompass all n qubits. In addition, process tomography is sensitive to all errors, including initialization errors when preparing the input state and measurement errors at the output, which, although certainly real errors, are unrelated to the quality of the gate operation itself. As a result, an alternative approach called randomized benchmarking has also been developed. Randomized benchmarking essentially interleaves the gate operation being characterized with a random assortment of other gate operations. Although half of the gates are chosen at random, we know what they are, and so we can predict the expected output state, assuming all of the gates were ideal. This is then compared to the same experiment, but with only the random assortment of gates, to see how much the error rate has changed when adding the interleaved gate. This change in error rate is then attributed to the interleaved gate itself. This approach is then repeated for increasing numbers of pulses in order to obtain a refined estimate for the average error per gate and thereby the gate fidelity. Randomized benchmarking is much more efficient than process tomography, and it's also insensitive to initialization and measurement errors. However, it only provides a net error rate without revealing specific error channels. However it's measured, a gate fidelity of 100% means that our actual operation perfectly matches the ideal operation. For example, no matter where our qubit starts on the block sphere, our actual X gate would perfectly rotate the input state to the correct output state. Now, as you might expect, it's generally not possible to achieve a perfect gate fidelity. There will always be some level of error, whether due to qubit decoherence during the operation, imperfections in the control pulse itself, etc. The goal then is to see how many nines, 2 nines, 99%, 3 nines, 99.9%, that one can achieve. The higher the fidelity, the closer it comes to an ideal gate. And as we'll see later in the course, achieving high fidelity is critical because it translates directly to 2 important aspects of quantum error correction. First, the fidelity must at least reach a minimum value, called the threshold, in order for the error correction to give us a net improvement in the error rate. And second, once above this threshold, the higher the fidelity, the less the resource overhead required to implement the error correction.